Okay, everybody, welcome to the MGF 1107 Test 4 Review Workshop, hosted by the Learning Commons. I'm Noah Schmidt. I'm a math specialist in the Learning Commons, and I'll be facilitating the workshop. And we're going to go over 14 problems that hopefully will reflect the kind of problems that you'll see on your Test 4 for MGF 1107. So the way this will work is I already kind of have all the writing out, but you can ignore the writing. Hopefully you can try to do that because a lot of these answers, it's more about understanding why these answers are the way they are. The reason I did all the writing beforehand is because with the amount of time we've got to do the workshop, it'd be difficult to get through the whole workshop doing all the writing as we're going, but I will explain it as we go. And that's more the important idea. But the way we will do this is I will give you a couple minutes on each problem to try the problems on your own. You just have to ignore the writing, or even if you just go through the problem and try to understand each question and how you would go about doing it, and then we'll go over them together. And then please feel free to unmute yourself if you have a question after we go over each question, or you can ask questions in the chat as well. So let's go ahead and get started. So the first question says, in exercises 1 through 4, we're going to use the following graph. So we got this graph right here, and we've got to find the degree of each vertex. We got to use the vertices to describe two paths that start at vertex A and end at vertex E. And then we're going to use the vertices to describe a circuit that starts at vertex B and passes through vertex E. And then we're going to list all the edges that are bridges. So let's go ahead and try this problem. I'll give you about 2 minutes on this problem, and then we'll go over it together. So if you're just getting in, we're just going through the problems on our sample practice test. So right now we're giving you guys time to try this on your own before, even though the answer is already written up here, you just try to, see if you could ignore the answer or just understand how the answer is being computed. But okay, so here's what this problem is saying. Find the degree of each vertex. So the degree of each vertex is basically the number of edges that go into a vertex. For instance, if you look at vertex A, there are 2 edges that go into vertex A. So A has a degree of 2. B has a degree of 2. C, if you count the number of edges that are going into C, there are 1, 2, 3, 4. D has 3. E has 2, and F only has 1. Part 2, or question 2, says use the vertices to describe two paths that start at vertex A and end at vertex E. So a path, this is not necessarily an Euler's path. An Euler's path basically has to go through every edge exactly once. This just, anything where you're traveling through edges from one vertex to another is a path. So for instance, I got a path that starts at A, and then I went to B, then to C, then to E. So that's a path that starts at vertex A and ends at vertex E. It's not necessarily an Euler's path, but it's a path. And then another path that I listed here was A, B, C, and then I went to D and back to E, and that's also another path. They're different paths, but each of them is a path that starts at A and ends at vertex E. 3 says use the vertices to describe a circuit that starts at vertex B and passes through vertex E. So basically on this particular problem, there's actually a circuit has to end where it started. So if you're going to start at vertex B, it's not an Euler circuit because it doesn't tell us that we have to go through every edge exactly once, but it is going to be a circuit. We're going to start at B and we have to finish at at B, but we have to go through vertex E, and that would satisfy those conditions. You start at B, you go B, then you can go to C, then to E, then to D, then to A, then back to B. That's an example of a circuit that goes starts at B, ends at B, and passes through E. And then list all edges that are bridges. Basically, for an edge to be a bridge, if you take that edge out, it would disconnect the graph. For instance, CF is a bridge because if you remove CF, then F, the vertex F, would be disconnected from the rest of the graph. And the graph would no longer be connected. So that's a bridge. If you remove that edge, then it disconnects the graph, is what a bridge is. So does anybody have any questions on this particular problem? Okay. Let's try this problem. So this should hopefully be easier to ignore the writing. This says draw a graph that models the bordering relationships among the countries shown in the map below. Use vertices to represent the countries and edges to represent common borders. So we're going to draw a graph to represent this map. And so you can just use the first letter of each country as your letter for the vertices. And then just try to draw edges between common countries that are bordering each other. So I'm going to give you about 2 minutes on this problem, and then we'll go over it together. And I'm going to actually draw some actual dots here for these points. Whoops, sorry guys. So if we start with France, I let an F be France, and you look at what borders France or Switzerland. So I drew a line from France to Switzerland. There's France to Germany. So France has a, yeah, France should have a line to Germany. Yeah, I've got to go ahead and draw that line. So here's France to Germany. Thought I already had that on there. France goes to Luxembourg, so we got a line from. Oh, I already have a. Yeah, I see it. Sorry, guys. I've got the line from France to Germany. There it is, right there. But the bottom line is France is bordering to Germany. It borders to Switzerland. It borders to Belgium, and that's pretty much it. So, and also Luxembourg. So there's 4 countries that France borders to. Switzerland borders to Germany, Austria, and France. So you see where Switzerland borders to Austria, Germany, and France. You go to Austria. Austria borders to Germany and Switzerland. So I have a line from, or an edge from Austria to Switzerland and Germany. You go to Germany. Germany borders Austria, Switzerland. Basically, Germany borders all the countries, it looks like. So, and so you pretty much draw a line from Germany to all the other countries. Belgium borders Netherlands, Germany, Luxembourg, and France. And we have edges going to all those countries from Belgium. So, and then the Netherlands is just Germany and Belgium. So the idea is when you're doing this map is you want to draw all the vertices and label the vertices with the first letter of the country, and then just look at the borders and draw an edge from each country to every country that it borders. And you just kind of have to keep track of which ones you've already done, but that's pretty much the idea behind drawing a graph that represents this map. So does anybody have any questions on this problem?
No, sir.
Yes. Yes, did you have a question?
No, sir, I didn't have a question.
Oh, okay. Let's try this problem. This problem says, determine whether the graph has, for each of 6, 7, and 8, we need to determine whether the graph has an Euler path, an Euler circuit, or neither. And if the graph has an Euler path or circuit, we're going to use trial and error or Fleury's algorithm to find one. Now you have to use Euler's theorem to determine if the graph has an Euler's path, an Euler's circuit, or neither. So you count the number of odd vertices to do that. But let me give you about a minute and a half on this particular problem, and then we'll go over it together. So you always want to count the number of odd vertices first. So A has a degree of 2. That's not an odd vertice. This is for, let me do this down here. B has a degree of 1, 2, 3, 4. That's not an odd vertice. C has 1, 2, 3, 4 vertices. E has 2. G has 3. And F has 3. So basically there are 2 odd vertices. So let's make a note of that. 2 odd vertices. So there's 2 odd vertices for this particular graph. And that means that if you have 2 odd vertices, you've got at least one Euler's path. You don't have an Euler's circuit, but you at least have an Euler's path. Now, the Euler's path with 2 odd vertices has to start at one of the odd vertices and end at the other odd vertice. So you have to kind of keep that in mind. Start at the odd vertices are F and G. We're going to start at one or the other. I started at G, but you could have started at F as long as you end at G. But I started at G, and then when you're doing these paths, you got to travel over all the edges exactly once. And so G, I went from G to E, and then it's a good idea to cross off your edges as you go. And then I went to C. So E to, then to C, then to A, then to B, then to D. There's more than one answer of how to do this is kind of what I'm trying to say here. Then we went to F, then to G again, then G to C, C to B, and then B to F. So what we did is we started at G, we covered all the edges, and we ended at F. We started at one odd vertice and ended at another odd vertice. It's just trial and error, basically. And basically, you just know where to start, where to end, and you just make sure you travel over all of the edges exactly one time. Cross out any edges as you go and list your letters, and then you get your path. But there's more than one answer, though, is the idea. So it's trial and error. And so number 7 says, well, we're doing the same thing. And if you count the number of odd vertices on this particular problem, there's 1, 2, 3 odd vertices there. So let's just, rather than writing all the, let's just make a little tally for the number of odd vertices. A is odd, F is odd, E is not, D is odd, C is odd, B is not. So there's 4 odd vertices. Euler's theorem says if you have more than 2 odd vertices, you don't have an Euler's path or an Euler's circuit. And that's why we have none here. No, none is, there is not an Euler's path and there is not an Euler's circuit. So any questions on the first 2 so far? First 2 of this. All right. The next one has 1, 2, the E is not odd, A is not odd, B is not odd, C is not odd, and D is not odd. So basically, this graph has an Euler's path and an Euler's circuit, but really an Euler's path is technically a circuit. So we don't really necessarily need to show both. What we do need to show, I mean, you could, but really the Euler's path that I chose is an Euler's circuit. And rather than listing 2 Euler's circuits, I'll just show you one Euler's circuit because this is always already a path as well. But an Euler's circuit starts at one vertice and ends at the same vertice and travels over all the edges exactly once. So if you're doing if you're determining an Euler's circuit, just start at one of the vertices and just know you have to end there. I started at D, I went to A, so that crosses off that edge, and then I went to C, that crosses off that edge. Then I went to E, that crosses off that edge. Then I went to B, crosses off that edge, and then I went to D, crosses off that edge, and it crosses over all the edges. We started at D, ended at D, and you can't go over any edge twice. That's something else that you really have to be careful of, is not going over any of the edges twice. You got to go travel over every edge exactly one time. Okay, does anybody have any questions? Okay, let's try this problem. Use Fleury's algorithm to find an Euler's circuit. So what you're really doing, it's trial and error. Just see if you can find an Euler's circuit from this graph that's not the same Euler's circuit. I'm going to give you a little bit more time on this one to draw the graph out, but if you could draw the graph out, ignore my numbers and see if you can find an Euler's circuit. I'll give you about 3 minutes on this one. And we'll go over it. The first thing to note on this particular problem is that there are 0 odd vertices. So that means there's an Euler circuit. There's a lot of edges here. So I'll show you the Euler circuit I wrote out. You really just need to, it becomes more clear where you're going as you go through. Really, when you start out, you can start out at any vertice, as long as you know where you have to end up. But you just need to make sure that as you go through your edges, you see how I numbered my edges here? You could cross them off, but I would number them, because if you don't number them, then you're going to lose, unless you're writing your letters out as you go. But that is kind of redundant to do that if you don't know you're going to, you might have to erase all your numbers and try again, because you might end up making a wrong turn at some point, and then you got to kind of start over a little bit. But most of the time, it's not a problem if you're not numbering your edges. It's pretty clear where you have to go. I started at A, I went to D, And then I could have gone really anywhere at that point. I went to C, then I went to B. See how I'm numbering these edges as we go. Then to F, and I decided to go to C, then C to G, and then I went to K, then I went to J, then to F, then to G, then to H, then to E, then to I, then to H, then to D, and then back to A, or then back to E, I mean. So as long as you know what you're trying to do, you really just can't go over any edge twice. You have to cover every edge exactly once, and you have to end where you started. If you're numbering your edges, though, it's just practice will get you to know where you can and can't go, because if you go over the same edge twice, then you're not going to you've made a mistake in your Euler circuit. But sometimes you might have gone to a wrong spot, and then you have no choice but to go over an edge twice. If that's the case, you kind of have to backtrack and figure out where you went wrong. But I usually just start all over. But once you really practice these, you'll get to where you just number your edges and you go, and it ends up being an Euler circuit. But you don't want to try to, there's more than one answer is what I'm saying. There's a lot of Euler circuits on this graph. So you're not looking for the one specific Euler circuit, you're looking for any Euler circuit. As long as it meets the definition of an Euler circuit, there's a lot of answers that are possible to find an Euler circuit. So does anybody have any questions on this? It's hard to illustrate because there's more than one answer. Your Euler circuit could have been different from mine if you found one. It's more the process of how you go about finding an Euler circuit that's more important to learn and cover in these reviews. So let's try this problem. This problem is dealing with an application problem. Given we got this graph here of with the North Bank, South Bank, Island A, and Island B, and the bridges represent edges. A says draw a graph that models the layout of the city shown in the map. B says use your graph to determine if the city residents would be able to walk across all the bridges without crossing the same bridge twice. Explain your answer. And then if such a walk is possible, where should it begin? Let's see if you can try this problem on your own. It's basically, I'll give you about 2 minutes on that. If you want to just wait till we go over it, that's fine, but I want to give you about 2 minutes to try it on your own, if you'd like. Okay, so basically there's 4 different places to mark as vertices. There's the North Bank, Island A, Island B, and the South Bank. And the South Bank can get to Island B with 2 bridges. So there's 2 bridges to Island B. South Bank to Island A has 2 bridges, so I've got 2 edges to Island A. Island A can also get to Island B with 2 edges, 2 bridges. Island B can get to the North Bank with 2 bridges, and then the Island A can get to Island B with 1 bridge that goes right here. So that's the map, or that's the graph that represents the map. And then to determine if the city residents would be able to walk all the bridges without crossing the same bridge twice, explain your answer. That's just basically, if you've got more than 2 odd vertices, you wouldn't be able to do that. If you got 0 odd vertices, you got an Euler circuit. If you've got 2 odd vertices, you got an Euler path. If you got more than 2 odd vertices, then you don't have an Euler's path or an Euler's circuit, and you wouldn't be able to do this. So we count the odd vertices. Island A is 1, 2, 3, 4, 5, has a degree of 5. That's an odd vertice. Island B has 1, 2, 3, 4, 5 edges that go in it. That's also a odd vertice. North Bank has 4 edges that go in it. It's a even vertice, so not an odd vertice. And then South Bank has 4 edges that go into it. It's basically a even vertice, which is not an odd vertice. So there's 2 odd vertices here. It's got an Euler path, which means that it is possible. We're going to say yes, it's possible. Now, the question for question C is, if such a walk is possible, where should it begin? It should begin at either odd vertice. So basically, it's got to either begin at Island A or Island B, because those are your odd vertices. So does anybody have any questions on this one? Okay. Let's try this problem. Given you have this floor plan here, we're going to draw a graph that models the connecting relationships in the floor plan shown above. B, use your graph to determine if it's possible to find your path that uses each door exactly once. And then if such a path is possible, where should it begin? And you also would want to explain your answer on problem B, although you wouldn't have to write it out on this. You just would need to know how you'd explain why you would be able to do it or why you wouldn't be able to do it. So let me give you about 2 minutes on this problem, and then we'll go over it. So it's pretty similar to the last problem that we just did as far as what you're trying to do. All right, so we've got basically A through G for our rooms here. We got A, B, C, D, E, F, G. Now A can only get to B. So if I've got A, I can only go to B. So there's A to B. That's one edge from A to B. B can get to A and to C. We already have the edge from B to A, so we have an edge from B to C. We go to C. C can get to B, E, or out the entire home, or out of the entire floor plan home, which was represented by the floor plan. That takes space. Anything that goes outside of this floor plan here goes to G. So C can get to B, E. So you got C to B, C to E, and C to G, because C can get outside. E can get to C, D, and F. So E, we got E to C, D, and F. And then F can get to E. We already have that. And then F can also get to G. So here's F to G. So that's our graph that represents the floor plan. Now, we count the number of odd vertices to determine if it's possible to find a path that uses each door exactly once. So basically, we want to count the number of odd vertices. A is an odd vertice. B is not. C is an odd vertice, so that's 2. D is an odd vertice, that's 3. And E is an odd vertice, that's 4. Now, Euler's theorem says if there's more than 2 odd vertices in a graph, then the graph does not have a Euler's path or an Euler's circuit. So therefore, we're going to say, is such a path possible? It is not possible. So does anybody have any questions on this problem? Okay. Let's try this problem. So draw a graph that models the streets of the neighborhood for a police officer who is to walk each street exactly once. And then B says, use your map to determine if the officer can walk each street exactly once. Explain your answer. For the sake of time, I am going to just go ahead and go over this one, because basically the vertices are going to be represented by the corners. So here's a vertice right here. I'll let A represent this vertice, B represent this vertice, C represent this vertice, D this vertice, and so forth. There's E, F, G, H, I, J, K, and L. And it's just basically just connecting all the edges, or connecting all the vertices with edges that are represented in the map here. So this is our graph right here. Now we count all the odd vertices. So where are odd vertices here? Well, B is an odd vertice. C is an odd vertice. H is an odd vertice. E is an odd vertice. J is an odd vertice. And K is an odd vertice. Well, because each of those vertices have a degree of 3. And so that's 6 odd vertices. It's not going to be possible to walk each street exactly once. It wouldn't be possible, because there's no Euler's path or Euler's circuit with 6 odd vertices in this particular graph. So does anybody have any questions on this problem? Okay, let's try this problem. This says, this one's not going to take really too long. I'll give you about a minute on this one, but this says, how many Hamilton circuits are there in a complete graph with 5 vertices? There's a formula for this, and the formula is n minus 1 factorial. Let's see if you can try that part on your own. So n is 5. That's how many vertices there are in the complete graph. And the formula to find out how many Hamilton circuits there are is to just take 5 minus 1 factorial. But that's basically 4 factorial. And 4 factorial is basically taking the number 4 and then multiplying by its next lowest number, which is 3, and then all the way on down to 1. So 3 times 2 times 1. Now 4 times 3 times 2 times 1 is 24 would be your result there. So does anybody have any questions on that one? All right. Let's try this problem. This says, this is basically about weighted graphs. This says use the table below that shows one-way airfares between cities. So what you do is you just take this table here and you connect all the vertices together where there's a way to, where there's an airfare. So like A, the airfare from A to B is 460. You got to have an edge from A to B, and you also have to have that edge labeled as 460. So let's go ahead and draw the see if you can draw the graph that represents this particular situation here. It's called, again, it's called a weighted graph because you're numbering the edges. All right, so to go from A to B, you got 460. To go from A to C, you've got 200. To go from A to D, you've got 210. Now then you go to B and determine what the airfare is from B to every other vertice. So B to A is 460. We've already got that labeled. B to C is 720. So there's 720 for B to C. And then B to D is 680. Now you look at C. C to A is 200. We already have that one. C to B is 720. We already have that one. And then C to D is 105. And really all the edges are labeled at that point. So if you determine D to all the other vertices, it'd just be redundant. So once you have all the edges weighted, then you have your weighted graph. So does anybody have any questions on this problem? Okay. Now what we've got is, and we'll go ahead and go over this one together. This is an example of weighted graphs of how you could you're trying to find the optimal circuit for a weighted graph. So basically, we got the same table we had on the previous problem. 15 says a sales director who lives in city A is required to fly to regional offices in cities B, C, and D, and then return to city A. Use the brute force method to find the optimal route. What is the total cost for this Hamilton circuit? So what you're doing here is most of the time they're going to give you all the Hamilton circuits. I mean, if there's 100 Hamilton circuits, and you won't get one that has 100 Hamilton circuits, but what we have right here is we've got 6 Hamilton circuits. They already have the Hamilton circuits listed here. And so basically, if you just basically calculate the total weight for each circuit, and the optimal route is basically the one that has the lowest value. In this case, the value represents the total airfare. But for instance, from A to B, so A to B is 460, and then B to C is 720, and I've already got all these listed for you, but that's what you're doing here is you're just basically going from A to B, listing the number, B to C, listing the number, C to D, listing the number, and then D back to A, listing the number. And then you add it up, and you do that for all the Hamilton circuits. And it turns out that there's 2 that are the optimal routes of all 6 of the Hamilton circuits. The lowest weight for each circuit is 1445, and there's 2 Hamilton circuits that produce that. A, B, C, D, or A, B, D, C, A, and A, C, D, B, A produce the optimal circuit or optimal route for this particular Hamilton circuit. So does anybody have any questions on this? So in all likelihood, they'll give you the Hamilton circuits, and then you'll have to determine which one has the lowest weight. You should hopefully get a problem exactly very similar to this on the test, or there might be a variation of it, but it's still the same idea. You may not get a airfare problem, but it would be a similar problem with the same application. All right, let's try this problem. This basically says use the nearest neighbor method to find a Hamilton circuit that begins at vertex A in the given graph. What is the total weight of the Hamilton circuit? So you start at vertex A, and you got to end at vertex A, but you have to go over every vertice exactly once for a Hamilton circuit. So that's the difference between an Euler circuit and a Hamilton circuit. Is in an Euler circuit, you got to cover all the edges exactly once and end at the same vertice you started at. For a Hamilton circuit, you got to cover all the vertices. You got to go to all the vertices exactly once and end at the same vertice you started at. So, but the nearest neighbor method has a certain method, and they tell us to begin at vertex A. Let's see if you can try to look at this for about a minute and try to see if you can find the optimal Hamilton circuit. The lowest weight, it's actually the lowest weighted graph you're looking for using the nearest neighbor method. It may not be the lowest weighted graph, but it's more the nearest neighbor method that has to be followed here. And you're just going to use the nearest neighbor method and then try to find the total weight of the Hamilton circuit that's given by the nearest neighbor method. So let's see if you can try that on your own before we go over it. So the way the nearest neighbor method works is you start where they tell you to start. They tell us to start at vertex A, so that's where we're going to start. And where we go next is determined by the lowest weight of any of the edges that travel from vertex A. So you got a 11, a 6, a 8, and a 5. We're going to go from A to E and take the 5 route. So I listed A to E, and then we go from E to, what are our choices? We can't go back to A because we'll have gone there before we need to. We got to end the circuit at A, and we got to get to all the other vertices before we finish at A. So we can't take 5, but our choices are 10, 9, and 8. We're going to go 8, and that takes us to D. Then my choices are to go, I can't go back to A, I can't go back to E. I could either go to B or I could go to C. And if I go to C, C has 4 and D would have 7. So I go from D to C, and that's a way to 4. And then we go from, we would either be going, we really have no choice but to go to B because we can't go back to A until we've gone to B. So if we look at our weights, and that's really the optimal choice too, because going from C to B, we've got a weight of 5. But you see that if we go from C to B, we've gone to all of them, and then we end up back at A. So then we go from C to B and then B to A, and that would finish our circuit. So the question is, what is the weight of this particular Hamilton circuit? Well, from A to E was 5. We got to add all this up. From E to D would be 8. From D to C would be 4. From C to B would be 5. And from B to A would be 11. And when we add all this up, we get 33 would be the total weight of the Hamilton circuit. So does anybody have any questions on this problem? Okay. Is the graph shown below a tree? Explain your answer. Let's just go over what are some characteristics of a tree. A tree has to be a connected graph. It cannot contain any Euler circuits. And you got to have one fewer edges than there are vertices. So if you look here, there's different properties of a tree. I would recommend looking at your notes, but really you just have to give one reason why it's not a tree to explain your answer. And really, it's not a tree because and this is actually not a Euler circuit. It's basically does not have a circuit. Is a circuit, or it is a circuit, not an Euler circuit. But basically, if you look here, you go from D to C to E back to D, you have a circuit there. And so if you have any circuits in your particular graph, then it's not a tree. And that's anywhere. If you can find a circuit anywhere on your graph, then you don't have a tree. And right away, I've got a circuit right here. Now, if I had removed CE, really removed any of these edges right here, then we would have a tree. But the fact that there's a circuit there, and then here's another reason why you could have cited. You could have said, well, there are how many vertices? There are 5 vertices, and there are 1, 2, 3, 4, 5 edges. So there's the same number of edges as there are vertices. So that's another reason why it's not a tree. You'd have to have 4 edges if there are 5 vertices for it to be a tree. So there's a bunch of different, there's a lot of different criteria that it has to meet to be a tree. This is not a tree, and there you can cite any reason that fits the description. What I used was that it has an Euler circuit, or it has a circuit, not an Euler circuit, sorry. But it's got a circuit, so therefore right away it's not a tree. So does anybody have any questions? Okay. Find a spanning tree for the graph shown below. And we'll go ahead and do this one for the sake of time, but a spanning tree is basically taking an original graph. And so I've got this original graph here. These marks are basically me removing edges from the graph. But what you're doing is you're taking an original graph. You're basically, the only thing you can do is remove edges from a graph. You can't add any new edges. You can't add any it has to be the same. You can't add, for instance, A doesn't originally go to E here. In order to find a spanning tree, I can't add an edge from A to E. I can't add anything to the graph, but I can take away edges. And if I take away edges, then I've got a subgraph. And the subgraph, after taking away these edges or removing these edges, needs to be a tree. And if it is, then it's a spanning tree. So basically, what I removed was I took the original, I just wrote out the original graph, removed these edges. Okay, so I removed BC. You see BC is no longer there. I removed BF. BF's no longer there. FG. There's actually there should be a G in this graph here. Sorry. Need to clean up this PowerPoint here. Here's G, but there is a G to J here. I removed the graph, so I removed from G to H, and from F to G, and from C to G. Removed from D to H, and then from H to K. Now, why would I remove all these? Well, here's the thing. I don't want any circuits. Okay, so right now, let's count how many vertices I've got. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, or 11, 12 vertices. So I've got I've got 12 vertices. Now let's count how many edges we've got. 11 edges. So I got 12 vertices and 11 edges. Well, that right away, that's a tree if it's a connected graph. And it is a connected graph. There's no vertice that's disconnected from the graph. So this is a tree. And because it's a subgraph of this original graph, it is a spanning tree. Because all I did was remove edges from the original graph, and I've got a tree. And if it's a subgraph that's a tree, by just removing edges from the original graph, it's a spanning tree. There's more than one way you could have done that. So what I'm really highlighting in this review is the definition of a spanning tree and what you're trying to do. You know, you just make the three main things to really look for is the graph needs to be connected. You can't have any circuits, and you need to have one fewer edges than you have vertices. And if you do, you've got usually if one of those things is off, then it kind of spills over to other things. For instance, if there's a circuit, then you might have one fewer edge, but then you wouldn't have a connected graph. So they all kind of go hand in hand. But what I usually look for is circuit, and I want one fewer edge than I have vertice, and make sure the graph is connected. And so, but what we have right here is a tree, and it's a spanning tree. So does anybody have any questions on this problem? All right, and then this says use Kruskall's algorithm to find the minimum spanning tree for the weighted graph shown below. Give the total weight of the minimum spanning tree. So here's Kruskall's algorithm here. You got A, B, E, D, and C. You got to have these 5 vertices. So what you do is you list out all the weights of all the edges in order from least to greatest. And you just basically draw your vertices, and you basically, so we've got 1, 2, 3, 4, 5 vertices. I need 4 edges. Once I've got 4 edges that don't have a circuit where the graph is connected, then I've got a spanning tree, and it'll be hopefully the minimum spanning tree using Kruskall's algorithm. So what you do is you pick you start with 2. As long as 2 doesn't produce a circuit, you can select it. So I'm going to go from D to C and add that edge. So here it is right here. D to C was added first. So you'll know when I'm adding these by when I'm writing the numbers. So D to C adds 2. Then I go to 3. Well, I can add that because that's going from D to B. So I add this edge. I wouldn't have a circuit yet, and I can't add B to C at all. But that's a moot point because B to C is 11, but the next number is 5. So can I add 5? Well, D to E is 5. That would be right here. I still wouldn't have a circuit. Now, there's only one more possible edge that we need because we got 5 vertices. I've got to have 4 edges. I've already got 3 of them. Now, if I added an edge right here, I'd have a circuit. If I added an edge right here, I'd have a circuit. If I added an edge right here, I'd have a circuit. So there's only one more edge to add, and that's from A to B. That one was 7. And so there's your minimum spanning tree right here. Okay. So if you're doing using Kruskall's algorithm, you definitely want to count the number of vertices so you know how many edges you need, and you just want to make sure you don't select any edges. Start with the lowest number and keep adding edges unless doing so produces a circuit. And once you have the required number of edges that you need, then you've got a spanning tree, as long as your graph is connected. But again, you wouldn't have those 3 do not go, you wouldn't have all 3. If you don't have one, then you wouldn't have a spanning tree. You'd have to have all 3 at the same time, basically. Connected graph, no circuits, one fewer edge than vertices. So you can look for all those things. Does anybody have any questions on this problem? Okay, well, that's good timing. I hope this review workshop is benefited you in studying for test 4. So please feel free to email me if you have any questions. I'm going to send out the recording of this as soon as we get off of as the workshop ends. I'll work on sending the recording out for anybody that wants to look over it again. And please feel free to use the procedures that were sent out the first week of class for receiving tutoring from the Learning Commons. And if anybody has any questions, please feel free to stick around. Otherwise, I hope you have a wonderful day, and I hope you do well on the test.